Welcome to qnawire.
Okay, so in this problem, we have a trapdoor that's being held up by a string, and we're supposed to figure out how much torque the string is applying to the trapdoor to keep it open. So we're going to start with drawing a picture because it'll be very helpful for this problem. So we have our trapdoor over here. So here's the floor, nice and flat. And we have our hinge here, and then the door is being held open. Then it's held open at an angle of theta equals 65 degrees. And the string is holding it open at the very end of the door up here, and the string is perpendicular to the door. The door is also being affected by gravity, so that's pulling it straight down. Put that here, force gravity. Yep. And then we are also given that the mass of the door is 16.8 kilograms. So M equals 16.8. And the length of the trapdoor is 1.65 meters. So we'll just say L equals 1.65 meters. So we've identified that there are two forces on the door, so there's going to be two torques. There's the force of the string and the force of gravity. I'm going to draw another picture for the force of gravity, one that's a little bit simpler. So we're just going to have the plain trapdoor here, and then we're going to have gravity pointing straight down. Now we're going to want the perpendicular component of gravity to the trapdoor, the component which is perpendicular to the trapdoor. So we want to look at a triangle that's like this, where it's perpendicular like this. So we know that the floor is like here, and that's theta. So here's our theta here. And if we do a little bit of looking and a little bit of trigonometry, we'll figure out that this angle here is also theta. And I can't really write it within the diagram, but we'll just remember that this angle is theta. So yeah, we need to figure out the magnitude of the torque caused by the string. So the trapdoor isn't moving, so that we know that the net torque is equal to 0, which means that the magnitude of the torque provided by the string, so we'll call that Ts, like we have Fs over in the diagram. So the magnitude of the torque provided by the string is equal to the magnitude of the torque provided by gravity. So what we're actually going to do is we're going to find the torque created by gravity. And then since the torque of the string is equal to that, we'll find the magnitude of the torque of the string that way. So if we look back at this diagram at the bottom left, and we take a closer look at this triangle that we drew. I'll draw it a little bit bigger. There's f of g again. And we have this part that comes out here and this part, and it's a right triangle. We determine that this is equal to theta. So that means that the component which is perpendicular to the trapdoor here, that will be f of g, or fg, times cosine of theta, which is a little counterintuitive because usually when we're doing torques, we deal with sine of theta. But we want the component of gravity which is perpendicular to the trapdoor. And with the theta that we're given, we end up using cosine of theta. So now let's take a look at the formula for Tg. Torque due to gravity will be equal to R. Well, normally it would be R times F. And normally we would have sine of theta, but we've already established that it'll be cosine of theta. So cosine theta, and our F will be Fg. So now we just need to figure out what R is. So we know the length of the trapdoor is 1.65 meters. However, we also know that Fg will pull down on the trapdoor in the middle of it. So that'll be halfway, half of its total length. So R is then equal to 1/2 times 1.65. And now we need to figure out what Fg is, because we don't have that yet either. But we do have the mass, and we do know that Fg is equal to mg. So that will be equal to 16.8 times 9.8. And so Fg is equal to, I had it written down, 165 newtons. So now we have everything that we need to figure out the torque due to gravity. So torque due to gravity is then equal to 1/2 times 1.65 times 165 times cosine 65. I'm pretty sure they intentionally made everything 65. So I'm going to scroll down a little bit and just rewrite that so that's a little bit neater. So torque due to gravity equal to 1/2 times 1.65 meters, that's our lever arm, times 165 newtons, our force of gravity, times cosine 65 degrees. And if you plug that into your calculator, you get torque due to gravity is equal to 57.4 newtons times meters. And because earlier we said that the magnitude of the torque caused by gravity and the torque caused by the string are equal, we can then say that the torque caused by the string is also equal to 57.4 newtons times meters. And that's how you do this problem.